Welcome to Unit 7 of our course, where we're going to discuss performance in IPOP and some of the optimizations that are implemented to improve performance. So as an overview, one issue with virtualization is it introduces a level of indirection, as we've seen, which can incur potential performance overheads for certain operations. In the case of IPOP, the sources of overhead include overlay routing, where we have messages that may go through log n hops on the overlay using greedy routing. The overhead associated with crossing from the kernel level packet virtual network interfaces to the user level router where IPOP is implemented. The overhead of packet processing at the user level, and also the encapsulation overhead. The fact that IPOP encapsulates packets in other protocols makes essentially less bytes available for the payload. But to give you an idea of the overheads of user level to kernel crossing and user level packet processing, this is an experiment that shows performance of IPOP and its current implementation in a C# language as a user level router using a TAP virtual network device. And here we have two nodes connected by gigabit per second Ethernet local area network. And you see in the first row here the performance without the virtual network, so this is the native performance, and latency for round-trip messages, bandwidth for IPERF, high throughput transfers, and then you see in the next line IPOP, where there's an additional overhead in round-trip message latency of the order of a few decimals of a millisecond. The bandwidth cap is smaller than the peak bandwidth, and this again comes from the overhead of user level processing and packet kernel to user level crossings. With security, there's an increased latency and bandwidth overhead because of the additional computational cost of implementing security mechanisms such as encryption and authentication. But in the context of intercloud computing, what you see here is another experiment where we deployed virtual machines on University of Florida, Amazon EC2, and the GoGrid cloud provider. And these are using the NetPerf benchmark to look at bandwidth, and this is the stream benchmark on the first two rows, and round-trip latency measured in transactions per second on the next two rows. And what you can see is, again, there's an overhead associated with a virtual network compared to the physical network, but it's relatively smaller than the overhead that you would see within a local area network. But these performance numbers give you an idea of the expected performance of a user-level network. Other user-level networks have been shown to achieve greater levels of performance, but this is the trade-off that you always have when implementing an overlay at the user level. So discussing some of the important optimizations that lead to this kind of performance levels in IPOP. One very important, perhaps the most important optimization is adaptive shortcut edges. And the goal here is to avoid the long log n overlay paths for nodes that are communicating frequently. And the overall approach is we detect nodes that communicate, detect that there's IP layer packets flowing from two endpoints, and they trigger the creation of an edge between them. So the way this works is independently at each node, the node observes and counts how many packets, IP packets, it sends to other nodes. Let's say NI counts packets that sends to node NJ. And upon crossing a threshold, this process triggers the creation of an edge between NI and NJ. And this can be a very small threshold of a few packets. And then these edges are monitored and connections are dropped if there's no longer traffic after a period of time. So we've seen the basic technique to create edges, and this is reused in this context. Again, A and B send their endpoints, they exchange endpoint URIs, and they try to simultaneously link over the physical network endpoints. So here, when A sends a packet to B, the first thing that happens, as we saw earlier, you look up the IP to P2P mapping in the distributed hash table, encapsulate the packet, send it via the overlay. Concurrently, A will send a connect to me request to B and initiate the linking process as discussed earlier. If successful, this creates a direct link between A and B, and the latency and bandwidth improves significantly because you avoid the long overlay path. Another optimization is builds upon the previous one in the sense that you would also want to avoid long overlay paths. But in some cases, the previous technique will not work because two peers may be behind nets that are not traversable, symmetric nets, for example. So the goal here is, instead of having a log n path between two peers, we will try to find one intermediate node between them. So the way this works is X and Y, being the two nodes communicating, will now exchange a list of their neighbor URIs, the URIs of their neighbors, and they'll try to find a common neighbor through which they can communicate. And the connection that they create with this common neighbor will be abstracted as what's called a tunnel edge, which looks like an edge. It's abstracted as an edge between X and Y, and the fact that it goes through a third, an intermediate node, is abstracted so it's not seen by the routing protocol. And the edge connecting X and Y allows communication to happen as if these two nodes were directly connected.